Hey everyone, welcome to the latest in Bitcoin Tech Club. Today we'll continue to discuss news items from newsletter number 363, Optech newsletter number 363. Uh, we'll try to understand about Frost signature scheme. It will be largely an overview of it, not too much detailed into it. Probably it will need few more sessions if you want to do a deep dive. Um, yeah, and one of our Bitshala fellows, Shivram, he works in this and he contributes actively to the Frost uh, libraries. So probably if people are interested, I can. If people are interested in a deep dive, we can probably arrange a session with them. Then we have RGB protocol. It's a smart contract protocol um, that that builds upon Bitcoin. So we'll also have an overview of it, not a deep dive on into it. So yeah, these two are quite involved topics, and we cannot do justice within the 1 hour that we have. So we'll have an overview, and probably we'll do more deep dives on in coming days. So yeah, let's begin with Frost. It's an abbreviation for flexible round optimized Schnorr threshold signatures. So um, we'll get into the details of it. Why it is called flexible round optimized threshold signatures as we move along. First, we'll have a brief overview about Schnorr signatures. So as you all know, Schnorr signatures was activated in Bitcoin along with the Taproot upgrade. So uh, we'll briefly have a look at the Schnorr signing scheme and the Schnorr verification scheme. Uh, so, uh, so, this is an overview of the Schnorr signing process. Um, just we'll try to understand this, and we'll as we move along, we'll try to compare it with ECDSA and how it differs and what advantages it gives with respect to ECDSA. So basically, the signing process happens along this direction. So you begin with the private key and a random set of auxiliary bytes and the message that you want to sign. So then what you do is that you derive the public key from your private key, and you also derive what is called as a private nodes. So it is a cryptographic process that involves hashes, and what goes into this process is your private key, your auxiliary bytes, and your message. So out of these two, you get your private nodes, and from your private nodes, you derive your public nodes. Um, then there is a somewhat of a different process where you create something called as a challenge. This is used to by its very nature. Schnorr signatures tend to be an interactive process where you do one step, you pass the information to the pass the information along, get back to reply, and then you continue. So by its nature, it's an interactive process. But in order to avoid this interaction process, people have created a process in which there is no need for an interaction, but the security properties do not get compromised anyway. So that's why you have this public nonce and challenge and stuffs. So once you get your public nonce and challenge, you put them in and you create your signature. So the basic signing equation is a simple equation, which is S equals K added to your private key times your challenge. So that's a simple signature that you have. So this is the signing process. Next is the verification process. As far as the verification goes, we'll start with the following items in our hand. We'll have a public key, we'll have the signature and the message. From this, we'll compute the challenge as we did here, and then we'll try to verify whether this equation is true or false. So you have your signature times your generator point plus this n minus e times p equals r. So this is the verification equation, and this is the signature equation. Um, uh, it's quite involved, this whole process. We'll have to spend more time in just trying to understand this two processes itself. We'll just try to have an overview of it. So you just try to keep in mind that this is the signing equation and this is the verification equation. Now that we briefly have had a look at the signing and the verification equation, we'll try to understand what how Schnorr is different from ECDSA. To begin with, first, there are some similarities. Both work on this use the same SEP 256 K1 curve, and both rely on the discrete log security. As you can see here, E times T. This is the discrete log security that Schnorr also relies on, similar to your ECDSA. But the differences are, if you can see, the Schnorr's signature equation is much simpler when compared to the ECDSA's signature equation. And Even though it doesn't provide you any computational advantages, the equations itself is simple, so that is considered as an advantage. Then this Schnorr signature is linear. That is, its construction allows it to add signatures together. Whereas in ECDSA you cannot add signatures together because it's not linear, and because there is an inverse involved here, and there is an multiplicative factor involved here. Elliptic curve multiplications are involved. It is not possible to add multiple ECDSS signatures, while you can do that with Schnorr signatures. Similarly, Schnorr signatures only uses arithmetic addition and multiplication. So you have an addition process and you have an multiplication process. But when you compare it with ECDSA, it uses modulo inverse and elliptic curve multiplication. And also Schnorr signatures are non-malleable in nature. You don't have this problem of forcing the user to select a low S, and which has been implemented as a BIP in the existing ECDSA signature algorithm. That problem doesn't exist with Schnorr because it is not malleable by its own nature itself. So these are the basic differences between Schnorr and ECDSA. As I mentioned, Schnorr is famous, or is preferred because of its linear nature, which means you can keep adding signatures. So in this example, I have shown you like the two signatures, S1 and S2. What you can do is that you can directly add these two signatures just by adding the K factor and pulling out the private key out, and adding the D's, pulling out the pulling the challenge out and adding the private keys together. So this comes out to be a very neat and compact summed up signature, which is no different than the original signature to start with. So you can see the same equation form to be maintained. So S equals K plus E times D. So similarly, when you aggregate it, it's also of the same form, S equals K times K plus E times D. So what this signifies is that even though you have now two signatures embedded here, it looks as a single signature. So that is an added privacy and memory advantage that Schnorr signatures bring to the table. So this is a brief overview of Schnorr signature and how it is better than ECDSA. The rationale behind choosing ECDSA by Satoshi, as most of you know, is that Schnorr was patent protected when Satoshi was writing the Bitcoin Core software. So he chose ECDSA, and since then, Schnorr's patent has expired, and now it's available for public use. And following that, the developer community have picked Schnorr up, and they have integrated it with Bitcoin. With respect to quantum, Schnorr and ECDSA suffer from the same discrete log vulnerability. So you have to, so Schnorr doesn't provide quantum resistance. You will have to look into other types of signatures like Lampert, etc., for quantum resistance protections. I'll pause for a brief moment if anyone has any questions.
Is it just the addition of keys Bala which makes Schnorr special, or is there more to it?
Yeah, basically, the advantages comes in many forms. Primarily, the simple nature of the signature equation itself, and then its linearity, which in turn facilitates or lets you add signatures together. So that is another advantage. And then also this Schnorr does not suffer from signature malleability issues that ECDSA inherently suffers from. So that is also an added advantage of Schnorr.
So, Bala, I had a question.
Yeah, yeah.
Yeah, so can you ask? So, if we want to add a quantum resistant to the actual blockchain, which is right now, do you need a hard fork for that? If you want to change it from discrete log algorithm problem to a signature which doesn't need it, will it need a hard fork?
Um, yeah, you have to like change the uh, no, if you just want to change the signing algorithm, you can do it with a soft fork. But if you want to like do if you want to care for coins that will not or there is no scope of them to be moved, then you'll have to think of some sort of an hard fork for it. So
So, so
like we created Schnorr, we could also create let's say Lampert. You'll typically have a new address type for Lamperts. It will be a new soft fork, and old users can migrate their coins to the new address.
So why don't the developers do it then? Because if you know that Schnorr and whatever the seed lock problems have with quantums, then we can do the hard fork whenever we want. But at least we can start with the quantum resistant signatures at least, rather than
Yeah,
talking about.
the problem is there are many unsolved problems with quantum resistant signatures like Lampert. Lamperts are one of the many candidates that are being examined and worked on. The problem with Lamperts is because they are hash based, they are very memory heavy and they consume a lot of the typical transaction that uses Lamperts are very 10x to 20x larger than what you have now with your normal ECDSA. So, that is that is a problem that has to be solved, and people are working on it. And there are many competing algorithms. Lampert is one that has some backing by the Bitcoin community. By Nova, it's a new scheme. It's a old scheme, but yeah, this process takes their own time.
Got it. Got it. Thanks.
Hi, Bala.
Yeah.
Is there any specific BIP through which people are working to integrate Lampert into Bitcoin?
Yeah, there is one BIP. Let me get back to an older.
Is there any other signature scheme also which people are working on or researching to integrate?
Yeah, there is this BIP called BIP 360. So that is up. So you can look into this BIP. Particularly Lamperts are being worked on. Apart from that, you have the only signature scheme that is being actively worked on by the Bitcoin committee is Lampert signatures. This
Mhm.
360 is about a separate P2 pay to quantum resistance hash. So it's a different address
Yeah,
type, and it has its own version. It has its own
I guess
design
to
and stuff.
migrate keys,
Yeah, to
it should
migrate
be
keys,
that.
it has its own design. It
Mhm.
but this is a lot more comprehensive, and it has a lot of like it is looking in. I don't know the specifics of it. What is currently happening in this BIP, but the BIP also looks into Sphinx, Falcon 1024, etc. So if you want to have, I would suggest you to follow this BIP to get an idea of what is happening. So this is the most famous and most actively worked on BIP in Bitcoin right now for quantum resistance.
Right, right. Have you given this talk, the one you are referring to,
Yeah. We did
this
it
particular?
like in week 27. Yeah, some
Okay, okay.
2 months back.
Right. Thank you.
Well, just an slightly different question on the topic. So here in the BIP 360, it says pay to quantum resistance hash.
Yeah.
So just curious, what would be the difference between normal address hash of a normal address and quantum resistant addresses hash? What would
Uh,
be the
Yeah,
crucial
but
difference?
the difference comes from the signing algorithm. So uh, anything like in order to be quantum resistance, first things first, we have to not use the elliptic curve based signature schemes. So that's where the that is where the primary attack vector of quantum lies in. So using there is a algorithm called Schnorr's algorithm in quantum computing. So Schnorr's algorithm is particularly developed uh, in order to reverse or break this discrete log problem. So yeah, that's that for any BIP or any quantum resistant address type, any scheme that you want to introduce should pick some signing scheme that doesn't involve ECDSA. So that's where the quantum resistance thing comes from. Whereas when you compare it with your normal address like pay to public key hash, pay to public um, pay to witness public key hash. They are all based upon the ECDSA signature scheme. So yeah, as far as the hash part goes, in the like every address scheme that you develop will have a hash in it. So that's what the hash represents. The QR, which is the quantum resistance, is made operational or is realized by using a different signature scheme.
Gotcha. No, it makes sense. Yeah,
Yeah.
because hashes generally, if I'm not
Yeah,
mistaken,
hashes
are
are
considered.
resistant to hashes are resistant to quantum attacks. Yeah, the
Oh,
QR
So,
so
is
Bala,
go ahead.
Yeah, Bala, follow-up question. So adding to your, so you're telling me that is it just elective curve, or as we discussed in the last cohort that it has to be, so discrete log problem with any signature will be a problem for quantum procedure, or only elective for discrete log
No,
problem?
the discrete log problem, whether you realize it using elliptic curve or some other curve, type of curve, if it has a discrete log problem, then if the security relies upon the irreversibility of the discrete log equation, then it is a vulnerability.
Ah, okay, yeah. So you mentioned elliptic curve especially, so I thought only elective curve discrete log problem has a quantum problem. Otherwise, so
No.
every log discrete log problem will have.
Yeah, yeah. Any, however you realize it, it doesn't matter if you rely on the security of the discrete log irreversibility, then it's a problem.
Okay, thanks, thanks.
Yeah. Yeah, that's about Schnorr and its advantages. Now we'll briefly have a look at what this threshold signing is. So that's where Frost comes in. We'll briefly, in order to understand threshold, we can like try to compare it with multisig, and it'll probably give us a good sense of what it is. Uh, these are two different types of uh, different architectures of signing, multisig and threshold. So in multisig, as you all know, we'll typically use distinct multiple private keys, and arrive at multiple public keys and a combination of them to sign your messages. Whereas in threshold, you typically will have a single private key, or a master private key, which is sharded or which is made into pieces and then distributed. And none of the participants can individually out of the algorithm arrive at the master private key on their own. So they have to like collaborate with each other in order to sign a transaction. So that's a basic difference between multisigs and multisig and threshold. Each participant maintain their own private key in multisig. In threshold, each participant just hold a share or one piece of a master private key, as you can call it that way. Then in multisig, as you all know, a transaction, take it from get a transaction signed by one participant, then move it along to the other participant and make him sign the rest. And then you'll have to there should probably be a coordinator that combines these partially signed Bitcoin transactions, PSBT, into a valid transaction and then broadcast. So that's how multisigs are typically work. In threshold signatures, the signal, you typically will have only one signature. The participants collaborate among themselves and arrive at a single signature. And on chain, this single signature you cannot differentiate between a threshold signature and a single Schnorr signature on chain. So that's a big difference. Multisigs typically operationalize their signature schemes using the Bitcoin scripting system, where you have object sig, which defines MFN threshold, and then it goes in and checks whether the threshold is okay and whether the signatures match the threshold private keys that is being provided, threshold public keys that are provided in the transaction. That's how it operationalizes this multi-sig scheme. Whereas in threshold signature, it's all cryptographic protocols and a lot of coordination goes on off chain. And finally, what you get on chain is a single signature, like this. So it is no different from a single Schnorr. So that is a basic differences between multisig and threshold. And Frost comes in. Frost is a protocol that comes in and defines how you can do all these stuffs in a very cryptographically secure and privacy preserving fashion. So you have to find these things read simple, but a lot of technicalities are involved when you have to go and split multiple private keys, and you should a lot of cryptographic overhead is involved when you want to combine it, and a lot of cryptographic overhead is involved when you when you want to sign them individually and combine them together. So yeah, so that's what Frost protocol is, where it operationalizes or defines how you can actually achieve this threshold signing process. So so we'll have a basic look at what a frost signature looks like. Then we'll probably we'll try to get into the protocol, frost protocol. So this let's say there are I number of participants in your I number of participants in your signing scheme. So so this is the signature that one participant produces. The first participant will take his private key, and then use his private key share. Uh, then he'll also, there is something called as a Lagrange coefficient that is used in order to combine the signatures together, and he'll produce something called something as termed as an ZI, that is his signal signature. Uh, Finally, the protocol, what the protocol will do is that it will try and sum it will sum these signatures up as one single signatures. So when the protocol finishes and you get a final signature, it will typically read like this, which is a summation of all the ZIs that each and every participant provides you. And if you look at it closely, the important point is that this summed up signature will look like a single signature. So that's the whole importance or significance of this protocol. That's how it leverages the properties of Schnorr signatures. Okay, now we'll briefly look into the two-round frost signing protocol. There is also a single round frost signing protocol, which is a much more improved version of it. Um, as the name says, it's two rounds. In the first round, you will go about generating the nonce and commitment in this protocol. Then you will generate the signature shares and finally combine the signature to get this single final signature. Um to begin with, what this protocol assumes is that the participants have, like, among themselves completed the distributed key generation process. That is, they have the distributed key generation process is something separate. We'll have to look into it separately in order to understand it completely. You can think of it as some sort of a opening ritual or starting ritual, where the participants coordinate among themselves, and finally at the end of the process they have their secret shares, that is SI, with them, and they also have a group public key. So now that they have done this process and each participant have their secret shares with them, they can go ahead and enter into this two round signing protocol process. So what do they do is that in round one, there will be a signature aggregator or a coordinator. Typically, is called as a coordinator or aggregator. He picks up the message that you have to sign. For example, in a transaction, it's inputs and outputs. So he assembles the transaction and creates a message that is to be signed. And and let's say there are n number of participants, and the coordinator, based upon the scheme agreed upon, picks T participants from N available in order to go ahead and continue with the process. So now that the T number of participants are selected, um, each participant will go about generating two random nonces. One is called as a hiding nonce and one is called as a binding nonce, DI and EI respectively. Then the once generated, the individual goes on to create a commitment, which is nothing but multiplying it with the generator point of your elliptic curve. So he gets a hiding commitment and a binding commitment corresponding to the hiding nonce and binding nonce. Now what happens is that the participants communicate, or they exchange their commitments to the coordinator. So um, uh, completes round one. Now the round two will begin. So now that the coordinator has all this information with him, so he will go ahead and compute something called as a binding factor, uh, which is nothing, which is denoted by the mathematical symbol rho I, which is nothing but a hash of yeah, your message, and B is the list of all the commitments that um, the participants have given to the coordinator. Then the coordinator goes ahead and calculates the group commitment using this uh, equation. Then after the group nonce is computed, then the challenge generation happens. He also computes the challenge, which is something similar to the single package distribution. The coordinator then also contains the message M followed by the list of all commitments. Each participant then computes their signature using the equation that we saw earlier here. So using this equation, now they compute their individual share and then send this back to the coordinator. The coordinator verifies these signatures, and then he finally aggregates it to get your Z, which is the sum of all individual signatures. So that's how the signature is created in this two-round frost signing protocol. It's a very top level, very top level overview. There is a lot more cryptographical math involved in the two rounds, and also there is a single round version available also. Yeah, probably we'll have to spend more time if we separately. We'll have to spend more time on this particular process in order to understand it very detailed fashion. Yeah, I'll wait for a few seconds and for any if you have any questions. Like I'm also not very super involved with Frost. Uh, I also have a very top level understanding of it. If we want like very super involved, then probably we'll have to bring in Shivram and we'll have to request a session with him.
Hi, Bala. That idea will be great. I have one question here. Like, is there any wallet in Bitcoin right now which uses Frost for threshold signing?
Um, No, right now I don't think so. Adoption is not yet up. People are still working on the scheme only. Last I checked, when I met Shivram, probably few months back, he was saying that they are like yet to bring the code to production level frost signing. So
Mhm.
yeah, I don't think there are any wallet. It's not that mature yet.
Okay, so is there any library that is being built to implement this functionality? Because Frost pretty much is like there are some versions to it which already have been accepted by some other blockchains as well. So,
Yeah,
uh,
for Bitcoin, people, I'll post the library that is currently being worked on. Uh, just a minute.
are you talking about chill DKG?
No, just a minute.
Okay.
Okay, I think I lost the library. I'll probably look at it and then I'll. Yeah, yeah, it's chill DKG. Sorry, yeah.
Mhm. Okay, so what happens when they develop this chill DKG? Will all the wallets that want to provide this functionality, will they be using that chill DKG to enable frost signing?
Um, no, for a consumer grade wallet like let's say Blue Wallet or something like that, they will
Mhm.
not be interested in Frost. So Frost will
Any specific
probably
reason?
it's too complex and their customer base or their user base will largely be using a simple pay to witness key hash type of address. At the max, they'll be using two of three multisigs. So even their customer base will not even be using a simple pay to taproot P2TR addresses.
But can
So
we
yeah,
not use this mechanism for multisig as well? For like
yes,
multiple separate distinct public keys?
yeah, you can use it, but like if you want, like if your question is, can you implement or use it in wallets? Yes, definitely you can. But if you are asking whether there will be widespread adoption of it, then probably no, because it's something new and people don't understand it, and a normal run in the mill wallet user will not be interested in a threshold signing process, or
Mm-hmm.
he will not be interested in the privacy benefits that it might offer to him. So yeah, adoption will be very specific to will be specific to use cases where, like, let's say there is a corporate setup where you have multiple signers, and they particularly don't like multisig because it's let's say they probably want more than 20 signatures in their threshold. You can't do it with a P2SH check multisig script. You probably have to move to a taproot, and within taproot, this frost will probably be advantageous for them.
So is the same applicable for the adoption of music as well?
Yes, yes, yeah. Music also is is like a very good stuff, but for the normal run-in-the-mill customer or a user, it doesn't make much sense for them.
Okay. Is that being used in any wallet,
Yeah,
commercial
yeah,
wallet, if you have any idea?
yeah, musics are widely adopted by like uh, uh, many exchanges have musics within their internal wallets. I know of if you have heard about the company called BitGo, they have a very they have adopted music extensively. We have um, one BitGo engineer with us, Saravanan. Largely spearheaded adoption of music within BitGo. Yeah, at the enterprise level, music has good adoption.
I guess then the same should be applied for Frost as well, right?
Yeah, enterprises will be interested in Frost definitely, and yeah, once the libraries are mature and there is enough testing and weightage behind it, and there are some like it's all it all depends upon the company and the type of developers involved in the company.
Mm-hmm.
It has to for like the developer has to have a good knowledge about it, and he has to push its advantages within the company, and then only then like that's how adoption happens inside enterprises. So like at that from the top level decision makers, I don't think they will be like very much willing to get into a new technology, because they'll be skeptical, and they'll operate from a perspective of if it doesn't like if it works, why are you trying to fix it? Yeah,
Okay.
that's where the top level people will be, but it's up to the um, engineers who are working to push adoption within enterprises.
Okay, okay. Makes sense. Thank you.
Bala, I had an amateur question.
Yeah.
So is this applicable to static addresses also, like for silent gaming?
Uh, this silent payments are something um, that is completely like you can do silent payments with whatever type of addresses that are available. At least that's what I think so. Uh, I may be wrong. I'm not sure.
Ah, okay, because
What
your
are
silent
silent
payment.
payments? Sorry, go
No,
ahead.
no, go
Sorry,
ahead,
what?
go ahead.
Yeah, I was wondering, is it like stealth address payment, silent payment?
Yeah, silent payment is a privacy feature that is being currently developed. What it does, on the top level, what it does is that when you put up a static address in your website, if it's a
Mm-hmm.
normal, let's say, pay to witness public key hash address, then the address is visible and anyone can track its on-chain activities. But in the case of silent payments, you will put up a static code on your website or wherever you want. But
Mm-hmm.
when you try to pay to that static code, internally what the
Mm-hmm.
algorithm does is that through a handshake and algorithmic fashion, what it does is that it derives a new address, a new pay to witness public key hash
Okay.
address for that particular transaction, and you will proceed with the transaction. When you try to do it again, you will get a new address. So that's
Okay,
how
okay.
that's how it
Stealth
that's how it
address,
works.
something like stealth address. Then I guess
Yeah,
Frost will be able to work with that. We can
yeah.
generate new addresses
It's
with Frost as
yeah,
well.
yeah. The as far as I can understand, silent payments are a top level protocol which can use whatever type of address you want to
Yes,
underneath it.
yes. Mhm. Yeah, so the individual addresses and individual actually key shares could be regenerated as per the new addresses which is being
Yeah,
generated.
true,
Payment.
true.
Yeah, right. Thank you.
I hope Apollo that sort of answers, but you'll have to check with the silent payments team to be sure whether they can
No,
do
yeah,
some.
yeah, Bala. So as Anubhav said, no, it is a little complicated than that. I don't think so because multiple signatures and coordination is required. So a little bit, yeah, it will be challenging because the chance payment changes and the wallet also are not implementing it. Right now, only I think the Cake wallet is implementing it. And that
Yeah,
also, the sender also has to have the same feature, or otherwise it is not one. So I don't think so. It will be a little complicated. I'll look into it. If you can share your links also, I'll be much useful. Thanks.
yeah. So next item, I think we are at the 9 mark. I don't think it's wise to get into this RGB today. So yeah, I think we'll call it a day with respect to the session. Yeah.